Today we're going to look at the quantum harmonic oscillator, a really sort of important problem in quantum mechanics. It's an important system to know and study. We're going to introduce it for a lot of reasons. Particularly, it's a nice sort of natural build on some of the potentials we looked at and solved in the last course in Physics 323. And we're also just going to sort of learn some new techniques with it. Let's sort of review classically what our harmonic oscillator is. So classically, let's just think of the canonical harmonic oscillator example where you have some mass m attached to a spring, and if you give it a kick or pull it to the side and let it go, it oscillates back and forth in harmonic motion, right? This is described by a force that's equal to negative k times the position x. So that pulls it back and forth. It has some potential energy that's equal to 1/2 kx squared. Um, and we know lots of things about this. We know the angular frequency is just going to be square root k over m. If we solve the differential equations we get from Newton's law, we get the harmonic oscillation position as a function of time with that angular frequency. Now, already we can use this, just the things we know, to sort of discuss why harmonic oscillators can be such a valuable system to look at different things, right? If we look at that potential energy, it's a parabola, and forgive my horrible drawing here. It looks like a parabola centered at 0 of 1/2 kx squared. Now, let's consider some other, whatever it is, more complicated system that has some potential energy that may look like this, right? And we want to look at, say, near an equilibrium point. Let's, choose this one. We're looking at that equilibrium point, x naught, right? And if we zoom in and look at the potential energy near that, well, that potential energy looks, like a parabola near that point, right? Mathematically, we could Taylor expand that potential energy as a function of x, right? It's going to be the potential energy at that point, x naught, plus the distance from that point times the first derivative of that potential energy with respect to x, plus the distance from that equilibrium point squared over 2 factorial times the second derivative with respect to x evaluated at that point. Forgot that one there. And so on. And we can Taylor expand this, right? We can do that about any point. And if we look at this equilibrium point, though, right, we see that it has this v naught x is just some constant value, right? But with potential energies, we're free to sort of choose what our 0 point is. So we can shift this whole approximation and say, all right, we're just going to call that 0 and set that first term to 0. Now, if we're looking at this x equilibrium point, the second term, well, by definition, if I'm near that equilibrium point, this first derivative is 0 as well, right? So the first term that's non-zero in this whole thing is the 1/2 x squared term, right? So if we can actually approximate to this order, 1/2 kx squared is what the potential energy looks like. And you see that from the plot. It looks like a parabola near that equilibrium point. And in this case, we've defined our spring constant is just the second derivative of that potential energy with respect to x squared, right? And x is defined as the position relative to that equilibrium point. So you can sort of see just from classical mechanics and what we already know about potential energies that all systems essentially near their equilibrium point can be approximated as harmonic oscillators. Now, what we're going to do in quantum mechanics is, well, remember the whole sort of one of our big goals of looking at systems of potential wells in that is to determine what the energy spectrum is. We want to know the energy eigenvalues and the energy eigenstates, and that comes into time evolution and a lot of other things. So our goal is essentially to solve that. And how do we do that? Well, the first thing we do is with these systems is we determine what the Hamiltonian of that system is. So for our harmonic oscillator, forgive me, we have some classical Hamiltonian. It's just the kinetic energy, the momentum squared over 2m, plus that potential energy, which is 1/2 kx squared. So we would take that classical Hamiltonian and we would then just write it in terms of the quantum mechanical operators, right? Now, one of the things we're going to want to do with this Hamiltonian is, well, we know that omega is equal to k over m, right? Or this gives us k is equal to m squared omega. We're going to actually replace k with that. If you think about a lot of the things we've seen in quantum mechanics, energies can be written in terms of h bar omega and all that. So it's a little more convenient a lot of the time to write that. So we're going to do that. We have our Hamiltonian is going to be equal to that. Um, oops, my bad. Misspoke and miswrote the k is actually equal to m omega squared uh, x hat squared. So we have our quantum Hamiltonian there. And our goal now is to solve our eigenvalue equation where we will determine our energy eigenvalues, our E sub n's, and our energy eigenstates. Now, in previous semester and earlier in last course, what we would do here is, well, we would just move to the position basis, plug in that we know our operator in that representation is IH bar d dx, um, and that our position operator is just the variable x. We would plug that in and we would get a differential equation for our, this amounts to a differential equation for our eigenstates, or our eigenwave functions, right? Where we would have those plus 1/2 m omega squared x squared equal to E sub n, right? And this is a differential equation where we could solve for our eigenfunctions as well as our eigenenergy E sub n, right? Um, we can do that. We're not going to brute force through it that way, right? Like that, there's a lot of differential equation. You do get there, you will get the right, after a lot of work and effort, you will get those eigenstates properly in the energies. But we're going to actually apply what we're going to call an operator method, which is a clever way of doing this, introduces a whole bunch of techniques, and turns out we can actually solve this problem using not much more than just commutation relations, right? So let's look at our Hamiltonian and see what we have here. We have h bar is equal to p hat over 2m squared plus 1/2 m omega squared x hat squared. So the first thing we're going to do with this Hamiltonian now is we're going to actually factor it, right, into terms. Now, easy first thing to do is factor out that 1/2 m omega squared, which will give us, well, let's just put the x term on the right, x hat plus p squared over 2m squared omega squared. Sorry, that 2's been factored out, my bad. So we have that term. And you know what? We can actually take this one step further, pull out an h bar omega off the front. And that gives us m omega over 2 h bar. And then we have x hat squared plus p hat squared over m squared omega squared, right? So this is just rearranging our Hamiltonian. And if we look at, the term inside the curly brackets, it's a lot like if we saw a difference of squares like this and we wanted to factor it, we would get a plus b times a minus b. And the difference in sign makes the cross terms go away. When we have plus, right, we can just throw in an imaginary I on that, and then the cross terms again sort of cancel and we're left with that difference of sum. So we're going to do the same thing here with our Hamiltonian. And to do that, what do we end up with? Well, this is going to give us, leave the terms in front, h bar omega. We're going to end up with square root m omega over 2 h bar times x hat plus I times p hat over m omega. And then the other term is going to be m omega over 2 h bar times x hat minus I p hat over m omega, right? But we have to be careful. So first thing, let's just name some things and simplify our lives. I'm going to call this one just an operator A, and I'm going to call this term an operator A dagger. And for reasons that will become clear later when we finish all this, we're going to call this a raising operator, and this is the lowering operator, and this the raising operator. You notice they are just simply complex conjugates of each other. Excuse me. So now what do we do with that? Well, like I said a minute ago, we have to be careful, right? The issue with, if we go back to this sort of factoring here, well, this ends up being a squared plus I b a, and then minus I a b plus b squared, right? And in normal sort of algebra, these would cancel. But these are quantum mechanical operators, right? So BA does not necessarily mean AB. There's a commutation relation here where there will be that leftover term here. So what we have to do in this Hamiltonian to make it actually equal the Hamiltonian we want is to get rid of that cross term. So how do we get rid of those cross terms, right? Well, let's look at what we get. Let's say we have A dagger times A. That's going to be equal to m omega over 2 h bar times x hat minus I p over m omega times x hat plus I p over m omega, right? And when we carry out that expansion really quickly, we get kind of what we were hoping for. We get x hat squared plus I x hat p hat over m omega minus I p hat x hat over m omega plus p hat squared over m omega, both squared, right? Now this first and last term, that's kind of what we were looking for. That would be our Hamiltonian, right? So that gives us our x hat squared plus p hat squared over m squared omega squared. But we have these cross terms, which are just plus I. That's the commutation relation between x hat and p hat over m omega. And from last semester and our Heisenberg uncertainty principle, we know that the commutation relation between the position and momentum operator is I h bar, right? So if we plug that in, right, we get our Hamiltonian that we wanted, p hat squared over m squared omega squared. This I is going to make this all negative. H bar is going to cancel this H bar. M omega cancels the M omega. And this ends up just being minus 1/2, right? So that's what A dagger A gives us. So if we want our Hamiltonian to be written in terms of these raising and lowering operators we got just by factoring this thing out, we can go back up to what our Hamiltonian was here. Hamiltonian is equal to h bar omega A dagger A, but to get rid of this 1/2, we have to add 1/2 there. So we've managed to rewrite our Hamiltonian in terms of these raising and lowering operators that we got just essentially by factoring that Hamiltonian. Great. So what does that get us? Well, let's look at a few more commutation relations and see what they get. First thing, let's notice that had we looked at A dagger instead of A dagger A, so rather than raising lowering, went lowering raising operator, The only thing that would have switched were these two terms uh, would have been the other way, and this whole thing would have amounted to the same thing, to h bar x hat squared plus p hat squared over m squared omega squared plus 1/2. We would have had to use the negative of that commutation relation. So we have those two. So we can actually look now at what our commutation is between our lowering and our raising operator. And it turns out, well, let's just take this, subtracting this, that's what our commutation relation is. That equals 1. So really quickly, we can go through just the same sort of thing and see that our raising and lowering operators don't commute. They have a commutation relation equal to 1. Another thing that we can do is look at how these things commute with the Hamiltonian. As we just figured out, the Hamiltonian can be written as h bar omega a dagger a plus 1/2. So if we wanted to look at the commutation relation between the Hamiltonian and the lowering operator, say, we can figure that out. That's just h bar omega a dagger a plus 1/2 a minus a h bar omega a dagger a plus 1/2, right? And if we carry that all through, just keep that h bar omega way out front, we have a dagger a plus a over 2 minus a dagger a minus a over 2, right? So these terms cancel, and we end up with h bar omega a dagger a minus a dagger a. We know the how to do these commutation relations, right? This can be written just as h bar omega uh, a dagger a minus a dagger times a, and this is just the commutation relation a dagger, but negative of that because we've switched the order. This is actually the commutation of a dagger a, not a dagger. So this means that the commutator between the Hamiltonian and the lowering operator is negative h bar omega times a. So we have that commutation relation. Similarly, if we did the other way and we looked at the other operator and did the commutation relation between the raising operator, this would just be h bar omega a dagger, right? So what do we have a couple commutation relations we've looked at with our raising and lowering operators um, in with the Hamiltonian with each other. We can actually use these to show the entire spectrum, and we'll see why they get the raising and lowering operator names from the commutation relations. How do we do that? Well, let's just sort of organize ourselves here, right? We have so far what are our commutation relations? We have the fact that h bar with the lowering operator is equal to negative h bar omega a. We have the Hamiltonian with our raising operator is equal to h bar omega our raising operator, and we had that the commutation relation between our two raising and lowering operators was equal to 1, right? So now let's remember our goal, right? We are trying to solve what the Hamiltonian acting on some energy eigenstate is. We're trying to solve that energy eigenvalue equation. To do this, let's take, for example, let's say we have some En eigenstate, and let's look at, well, how does that, if we take the lowering operator and act on that, well, that's just going to produce some other ket we're going to call A, right? So the lowering operator acting on an energy eigenstate produces some other state A, right? And we can ask ourselves, well, what is the Hamiltonian operating on that ket do? So what does Hamiltonian operating on A behave like? Well, since A is just the lowering operator acting on En, it's going to look like this, right? So how does this work? Well, we know from our commutation relation, right, that this HA is equal to negative H bar omega A. And by definition, that's HA minus AH. So that Hamiltonian times the lowering operator can be written as just AH minus H bar omega times that lowering operator. So we can substitute that in here and we get AH minus H bar omega A, all operating on that that energy eigenstate, right? Or just written in a way that I think makes things a little clearer, E sub n, right? We know from our energy eigenvalue equation that the Hamiltonian acting on that state is just E sub n times that state, that eigenstate, right? So we can rewrite this as that. And then since this E sub n here is now just a scalar, we can factor all these things out and we get this is the energy eigenvalue minus H bar omega times the lowering operator acting on En. And recall, this whole thing was just H acting on that ket A, which was A times En. And if we look at this, what we notice is this is actually an eigenvalue equation, right? H, the Hamiltonian acting on this vector, or this state vector, gives us some constant, some eigenvalue times that state vector, right? So what we're seeing here, and the eigenvalue is H bar omega below what the eigenvalue of this is, right? So you can hopefully kind of see what this sort of thing is. We have the Hamiltonian acting on that vector. Well, that is a vector that is just En, has the eigenvalue En minus H bar omega, and its eigenvalue, as we just said, is lowered by one sort of quantum of energy for that harmonic oscillator. Oops. Right, that's an energy eigenvalue equation. We know now that that lowering operator acting on E sub n gives us a vector that's proportional to En minus H bar, the eigenvector En minus H bar omega. We lose a bit of normalization. We'll have to check back on that and fix that later. But hopefully we can see why this is called the lowering operator, right? If we take the lowering operator and act on an energy eigenstate, what we get is a vector that's proportional to the energy eigenstate that's lower in that spectrum, right? So we have some energy here, we act on that state with the lowering operator, it lowers it to the state En H bar omega type thing. If we do the same thing but with the raising operator, what we end up seeing is that that vector ends up being proportional to En plus H bar omega, and it raises it up one sort of rung on our energy spectrum the other way. And this is actually sort of quite useful, right? One of the things, we've sort of seen that we can create, we start with some, given some energy eigenstate, we can just use these raising and lowering operators to sort of walk through our ladder of states, right? We could keep doing the lowering operator and moving down, the raising operator and moving up, and sort of figure out what those whole spectrum is, but we need something to start. And how can we find that first energy eigenstate? Well, if we think about it, if we think back to our infinite potential well, we had all these states, you know, the n equals 1, n equals 2 states, but there's some minimum state, right? We can't go below the bottom of the well. And the same thing happens with these raising and lowering operators in the harmonic oscillator. We can essentially say that there's going to be some lowest energy state that if I act on, if I try to operate on the lowering operator on it, I can't get anywhere, and that actually equals 0. This is sort of the ladder termination condition, is what it's called in the text. Um, uh, so what we can do is we can sort of take this condition and use that to give us our a place to start when we to figure out this spectrum, right? So let's, you know, acknowledging that there is that lowest condition, let's take our Hamiltonian and operate on that state and see what we get, right? We're trying to figure out what that lowest energy state is and what its energy eigenvalue is. And we're going to do that, right? So to do that, well, we know our Hamiltonian is h bar omega a dagger a plus 1/2. And if we act on E lowest, right, this ends up being equal to h bar omega a dagger a E lowest plus 1/2 E lowest, right? But because of this ladder termination condition, this term is 0. The lowering operator acting on that gives us 0. So this ends up being h bar omega over 2 times E lowest is what our Hamiltonian on E lowest is. So we've got, you know, sort of remarkably, we've determined what the lowest energy eigenvalue is for our ladder operator without actually solving any differential equation, just sort of defining these raising and lowering operators from our Hamiltonian and using their commutation relationships to get here, right? Now, to get the rest of the spectrum, we would just say, okay, so we have our E equals 0 state has an energy of h bar omega over 2. This is called the 0 point energy. It's the lowest energy you can have in the system. We could operate on our raising operator and get to E1, and that would be just h bar omega over 2 plus this h bar omega there. So plus h bar omega. And then we could use the raising operator again to get to E2. And that would be h bar omega over 2 plus 2 h bar omega, and so on and so forth. So we've really figured out the spectrum of our harmonic oscillator is h bar omega n, whatever level we're in, plus 1/2. And all of that came from essentially just looking at these commutation relationships as well as our ladder termination condition. So now we have we've got a lot done, right? We've got our energy eigenvalues here, define some n, so we can actually define, you know, right, our energy eigenstates. They're defined by that quantum number n there. And they're going to have the same sort of orthonormal properties that all our other Hamiltonian states has, where they're orthogonal to each other, they're normalized, all of those things. And we're going to use these a lot. One thing we can look at is our Hamiltonian is defined, you know, h bar omega a dagger a plus 1/2 here. We can define another operator, a dagger n, because, you know, if we take this Hamiltonian and apply it to our energy eigenvalue equations, we know that this is going to be, again, h bar omega A dagger A plus 1/2 acting on N. That gives us the eigenvalue h bar omega N plus 1/2 acting on N. We can define this operator. We'll call it the number operator, A dagger A. And it has the eigenvalue equation that N acting on an energy eigenstate pulls out the quantum number essentially of that harmonic oscillator and just tells us the N. So you can see how this, excuse me, well, you can hopefully just see that these operating on that give us that N value there, which allows us to rewrite our Hamiltonian in terms of that operator if we want h bar omega N plus 1/2. So to recap, what we've done is we've discussed the harmonic oscillator in quantum mechanical terms, derived a Hamiltonian for it. We defined these two raising and lowering operators here, and using only essentially the commutation relations between those operators and the Hamiltonian, we were able to derive the entire energy spectrum of this system. It may look kind of familiar to you if you recall the energy of photons and things like that. This comes up in a lot of places in physics. The one thing we haven't done yet, though, we've solved a good part of this problem. We've got the energy eigenvalues. Next video, we're going to go through how we can actually continue with this operator method and determine what those energy eigenstates are and go on from there. It's a really powerful tool. We're going to use it later in the semester as well when we start to talk about angular momentum and things like that. But hopefully you followed along. If you have questions, bring them up in our synchronous sessions. We'll have homeworks. As always, you can also reach out to me through email or through the course webpage, any difficulty you're having. And I will see you in our synchronous sessions.